Okay, materials experience shear when the force is applied parallel to one of the faces. So if you have a side view of an object, let's say a kind of a box or a book or something sitting on the table, and the bottom is held rigid, so the bottom cannot move, the bottom of the block cannot move, and a force is applied on the side, so it's applied on the top surface. The top surface is pushed to the right. What we would expect is that the thing would sort of twist a little bit and become like this. So this would be the new shape of that object. And if the original height is h and this is delta x, the amount by which it has moved is delta x, then the strain is written as a delta x over h, and the stress is written as a force over area. So the force is here and the area is this area. So if you see it from a little bit on the side, so that was the object initially, and let's suppose that the force is pushing it this way, then this is the surface area A, and the final shape would be this would deform and stretch out a little bit to the side, and this would come here. So this would be the new shape of this object, sort of twisted. So this surface area becomes the area for use with stress. And then we have the shear stress written as an S, is a stress over strain, becomes F over A over delta X over H. And the value of the shear stress is also of the order of 10 to the power 10 newtons per square meter. Again, it's of course different for different materials. Now the last one we deal with is the bulk modulus. So in the bulk modulus, if we take an object, let's say we take a cube and we squeeze it from above, we apply a force from here, and we apply a force from below, and we apply a force from the right and a force from the left and one from the front, so that's coming from the front and pushing inwards, and one from behind that's pushing it towards the outside or towards us. Then it's pushed equally from all sides, and the result would be that this object would, if the forces are strong enough, it would become smaller. Well, maybe not so small, but could be so small, depends on the bulk modulus. So we have an initial volume and we have a final volume, and so we have a delta V, which is final minus initial. So there's a change in the volume, and the strain is written as a delta V over V. So that would be the strain, and the stress would be the force divided by this area, this force divided by this area, or this force divided by this area. So it's a force by area, and that's a pressure. You could also add all the forces in all the areas, they still be the same. So this is normally a pressure, and usually this phenomena takes place when you have a deep container and you take an object here and you drop it in the water. Then the water pressure, which exerts on all sides, squeezes that object and makes it smaller. So we have the bulk modulus as stress over strain. So we write it as F over A, which is the pressure, over the strain, delta V over V initial. Now, because there was also an atmospheric pressure here, which was smaller, and a bigger pressure here, so we can write that as a delta P. And so we could say that the bulk modulus is stress over strain, and we put a negative sign to account for that, because this would be negative. When the pressure is positive, this would be negative, and so the bulk modulus comes out positive. Now, all of these moduli, or this one also, are of the order of 10 to the power 10 newtons per square meter.